This is AP Physics, assignment on RC circuits. Problems 34 and 35. 34 is a simple RC circuit, single resistor, single capacitor, and a switch in the battery. A, time constant. B, calculating the charge. That's C equals Q over V. And then C, you're calculating the current when you're charging. That's just pulling the charging equation. Okay, essentially you are at two time constants, and so the exponent negative t over RC reduces down to just a -2, and it's just a matter of plugging in values. Remember, the I naught in the original equation by Ohm's law is just the EMF over the resistance. 35, you're calculating the current at 9 microseconds, plugging into the equation. Again, keeping in mind the expression you have there in the equation, I naught, that was E over R, and then the EMF would be related to the maximum charge, which was Q over C, and so that gives you Q over RC there. And then it's a matter of plugging in the values that we have. Make sure you change your kiloohms into ohms. Part B, the charge. Again, you are discharging the circuit, so you're pulling that equation for the discharging, plugging in values. And then C, that maximum current value, that's a Q over RC that we used back in Part A. Number 36. You're dealing with RC circuit when you're charging. You know what the voltage is at 3 seconds, and you want to solve down for the resistance. So we're pulling the current equation when we're charging, and again, I plugged in EMF over R for I naught. To go to a voltage equation, basically if we divide the R we rewrite the current, I of t, as a V over R from Ohm's law. Okay, then we can just eliminate the R in the denominator on both sides and quickly move into a voltage or a V of t equation. From there, plug in all the values you have. That leaves the unknown resistance up in the exponent of base E. It's a matter of doing the algebra to solve down. Divide both sides by 10 volts. Take the natural log of both sides to eliminate the E, and then do the algebra to solve down for your R value. Number 39, dealing with an RC circuit with two different resistors in there in two different locations. Okay, in A, you want the time constant before the switch is closed. That's an RC. Okay, both resistors are in the connected path, so they are acting in series. So then the R you're plugging in there is the total of the 50 kilo ohm and the 100 kilo ohms. B, after the switch is closed. Well, after the switch is closed, the capacitor has already charged, and now it's discharging. The discharging is going to occur across the path where the switch is. So then the only resistance in that loop over here on this side, the only resistor there is R2. And so the time constant has only an R2 value in when you calculate that. Part C, switch is closed at t equals 0. You want an I of t equation in the switch. What you have to recognize is there's two things driving current across that center branch. There is a complete loop on the left side with the battery, and there's a complete loop on the right side with the capacitor and R2. So then your total current there is going to be a sum of the current from the battery and the current from the capacitor. The current from the battery is a constant. Ohm's law, it's just going to be an EMF over R1. The current from the capacitor is going to be your I naught e to the -t over RC from that small RC circuit discharging one. And so then putting those in, and then it's a matter of plugging in the different values to reduce the equation to an I of t equation. 41, you have a charged capacitor. You know the time constant is 1.5. Okay, and Q of T, you want it to be at 75% of the maximum charge. So we start with our Q of T for discharging. Okay, and we're going to replace that Q of T by a 0.75 Q. Okay, replace the RC then by a 1.5, and then divide both sides by Q and do the algebra to be able to solve down for what that time value is at which you reach the 75% of maximum charge. In B, you want to know the capacitance. You know the time constant. That's just a matter of plugging into that equation.